Excellent. Welcome to part 2 of the R tutorial. There were a few things left over from yesterday in part A that I wanted to make sure we covered. And these include loading data from a table. I know it sounds really exciting. It's a very essential skill, and I hope that we can cover that today. Has everyone made a copy of the R training materials on your computer? Good? Okay. So I believe that we stopped about here. We had just run the Pythagoras function for finding distances between points. But now we're going to start looking at something called DF transcripts CSV. Those data should appear in the training data right here, dftranscripts.csv. If you'd like to read the fuller story of the experiment that produced them, you can find that in the PDF file that I've included here. And there's also something to describe the FINA data that come with it. If you were just looking at the TSV file in an ordinary way, you might simply hit enter on it, which would probably open up Excel, and then you would get something that could be formatted very badly or formatted very well. In this case, it didn't automatically import it the way I would have expected, because this is a CSV file. Everyone know what CSV is all about? Comma separated values. If I drag it here, it's going to be unpleasant to me. So I'm now going to open it this way, and I keep expecting it to give me the wizard saying, how is it delimited? It's not behaving itself. So I'll do it the old-fashioned way and simply go to the Data tab, specify text to columns, specify that it's delimited by commas, and now I should automagically have columns to work with. Great. So these are what the data look like behind the scenes. We have particular genes and gene IDs, and we have FPKM values showing up here. And we specify that these are transcripts. It has an identification tied to it. Then fold change, p-value, and q-value. Everyone sees that at the top? Oh, it's way too small, isn't it? I'm sorry. So I can change the view side here. So let's make that 200%. Great. So I want to talk about these two because these are really, really common features in differentiating one cohort from another. Typically, you're going to have some sort of statistical test that says, are these expression values from one cohort to the other cohort different, or are they not? The p-value says, by random chance, oh my goodness, I'm going to try to give this definition. It's one that that has all sorts of little details that I can get wrong, so I'll try to be careful. The p-value asks, what is the probability that under random conditions, if there were no differences between the cohorts, that we would see samples this different from each other? So that is the p-value here, and we then applied some sort of multiple testing correction, a subject that is near and dear to my heart, but which we're not going to get into today, that handles the fact that we've asked lots of questions of a lot of genes of, is this different or not? So these p-values are about this gene if viewed in isolation. The q-values, just to the right, are about if we are able to take into account how many genes we've asked this question of. So it's a way to adjust for the fact that we made multiple difference tests. All right, and finally, fold change, which is essentially saying if we compare the total signal for this gene in cohort A to that in cohort B, what's the ratio between the two? All right, that's a fold change. So these are, this study in particular is not one that's about developmental biology or about aging research. It's, if I remember correctly, an assessment of changes in X and Y chromosome stuff. So if you want the fuller details on the paper, feel free to read it. I include it because it's a really common data type that we end up using in our scripts. So talking about some basic ways that we test and visualize these data, I think is very useful. All right, so just remember that behind the scenes, this is the table that we're working from. At the bottom of the RA Essentials of R Programming and File Access, at the very bottom of the file, this is the one we were looking at yesterday. I want to come back to cover this text down here. So I'm going to start by running this line, transcripts, read table, blah, blah, blah. I run it and immediately I get an error. So I gave you the script, assuredly it works, but here we are immediately getting an error on things. And this brings us to the topic of current working directory. Has anyone heard of this concept? Current working directory? Generally speaking, software says, this is my home place in the file system, right? So this is my directory. We can ask in where we are, but one of the things we typically do is say list files, list.files with parentheses there, and you can see that it's looking at custom office templates, desktop INI, my music, my pictures, my video. It's not where I want it to be. It's sitting in the wrong working directory. So I need to tell it where it can find this df tables. So I'm going to use the file change dir option up here. This is going to allow us to change to the location where the files may be found. So I've thrown these in archives Groningen and down here. Now my path is different than yours, so I can't really tell where you put it on your stuff. Why am I not seeing it? It's awkward. Oh, here it is. I've got them sorted by date modified. That's what's going on. All right. So if I want to look at them in file order, then I can go to Create Proteomics in R, Proteomics in R Biostatistics Training, and then I select that folder. Now when I say list files, I see the stuff we're supposed to be working with. So that's good news. Now, let me try running. Oh, let's talk just a moment about how to save time typing. If I use the up arrow on the keyboard, it tells me the last thing I typed. If I hit it again, it's still on list files. But if I keep hitting it, I finally get back to transcripts, read table, blah, blah, blah. That's what I want to run. I run it, and it tells me absolutely nothing. Well, we used the read table function, and we provided it with a few named parameters. The file is df transcript CSV. We set the value of sep to double quote, comma, double quote, and we specified that the file has a header. So what does that mean? Well, remember we said that the columns in our table are separated by commas. So I needed to specify that the separation character that's used to differentiate one field from the next is a comma. So that should appear directly in the script that I gave you a copy of. It shows up right here. So if you're having trouble finding it, that's where you find it. Is everybody able to load the copy of df transcripts on your computer? If you're using RStudio, there are some slight differences in how you would do this, because you would create like a project for this, a project folder, and put everything that belongs to it in that folder. But in this case, we're just using basic R to do the example. Yes, your question? It has not loaded correctly, so let's take a look. Okay. Right? Having changed to that directory. Look through file. Yeah, go to file, change directory. All right, tell it where the data are, and then you just found it. Is it the R course? Oh, yeah. Okay, try running. Hit the up arrow on your keyboard. Right there. Excuse me. Nope, not sure. All right, this is the up arrow. If you hit it, type list files, list dot files, in parentheses. Okay, so you need to change into the proteomics and R biostatistics training. So put back up to change directory. Yeah, into that. That's right. Okay, now put that there twice. One. There, good. All right. We were in the directory that holds the proteomics and biostatistics training, but not in the subdirectory itself. So that was a difference. Great. All right. Yes. Sure.
That's amazing French.
So much.
Okay.
So you've got you have some files copied. Okay. All right. And I need you to open text editor in that file. Notepad is not. Okay, good. Now you need to tell R where to find the correct directory. So it's here. Changer the now locate the directory again. That's good. Now you should be able to write this as well. The down table one is down in the bottom. So we're going to copy this one. Then use that in our session. Okay. Has everybody been able to load the table on your computer?
Yeah.
Within R.
Oh, and when I get it, but then when I unread the mark, nothing happened.
It's when it works, it just gives you the next part. So how do you establish that the thing actually loaded? Let's take a look at that. Okay. So we're going to start with my very favorite function of all time, summary. Okay. We seem to have construction noise. All right. So the transcripts object has been created by read table. And when I run summary on it, I see all the different columns. You should see the same column headers as you did when we looked at it in Excel just a moment ago. So gene names is here. There are 2,860 of those. Gene IDs are here. We have FPKM measurements. If I remember my RNA-seq, that's what fragments per kilobase per million reads. Is that right? Sorry, somebody who's more current in transcriptomics can correct me on that. But each of these is some sort of quantity being measured in RNA-seq from a different sample. And at the end, we have feature, ID, fold change, and all of that business as well. Let me rerun the summary here. So, okay. So at the very end, we have fold change, p-value, and q-value. That should all be there. So are you able to run summary on the object? Good. Good. This is great. I tell you, the thing that always trips me up in this training is getting R to the correct directory to read the file. So you're doing great. This is good news. Okay, lovely. So what can we do with it? We can run the summary, which we just did. But I'd like to talk about a couple little functions that are borrowed from Linux called head and tail. Head and tail are very useful when you have a ginormous table and you want to see some example data in it. Head is going to show you the top of the file. Tail is going to show you the bottom of the file. Now, where did these headers, feature, ID, FC, p-val, and q-val come from? How did R know to label those fields with those names? Remember when we ran read table, the very end of the line said header equals true. That means that R is using a reader that expects the top line to give a name for everything that appears below. So those names didn't just come from nowhere. They came from the header of the text file. So that's good news. We're able to read it, and that's very valuable. Yes? No. Excel has no effect on it. If you did overwrite the file by saving it in Excel, that's probably going to change the formatting. Would you like a copy of the original file? I'll bring the thumb right over to. Okay, you didn't say anything. Okay. With this session file. So we need to. Can you simply what's in open verify this because we're using our studio in particular. Yes. Oh, we're going to grab that. So I'm going to go ahead and also down. Yeah. The moment it's not seeing the file in your working directory, sorry. Oh, of course. Yes. Yes. Okay. Please have a question. You can. You can use read CSV, and it's the same thing. The difference is that read CSV will assume you're using comma separators. If you do read TSV, what's it called? It'll assume you're separated from characters with that. I just always use read table and specify option, but then there's no difference. So we've obviously picked up a noise source, and we're going to do the best we can, but hopefully we can change. Yeah, I don't know which room we would switch to, so I'm going to just stick with this one for the moment. Okay. No worries. Okay. So if you want to just see a little bit of the table that you're working with, head and tail are very useful for seeing the top and bottom of the file, essentially. As we continue, we have some valuable things we can learn just about how big is the table we're working with. And for this, I'm going to use the dimension function, dim, and it's going to tell us that how many rows we have and how many columns we have. When you have a really huge table, those dim functions are pretty useful for grabbing out the sizes of them. All right. Now, because this is a multi-dimensional data object, we probably want to do some things that allow us to grab out particular elements of it. And we talked briefly about this with matrices yesterday, but I wanted to give the example that if we wanted to grab out a particular line, in this case, line 13, we can specify 13, comma, to indicate just the 13th row, but all fields from it. So if you wanted to grab just the gene name from the 13th row, you might say transcripts 13.1 instead. In this case, we're giving the address of the whole row. In this case, we're using the address of a particular cell in that row. Does that make sense? Cool. All right. So when you see that type of indexing used, that's what's going on behind the scenes. All right. Now, a function that I used a whole lot when I was first doing coding in R was subset. Now, subset is a really handy function that pulls out of a really big data object just a few lines that meet a certain criterion. In this case, I don't know which rows match m string 11, but I want every row that meets that criterion. Remember the equals equals rather than single equals? So this is saying if G9Ds is equal to this string, then this row qualifies. I want to grab it. So I can subset from this and even shove that into a different variable. And what we see is that in this case, 4 different rows from the table all match this m string .11 name. Okay? If you like to move up closer, that's fine too. Oh, I often have that look on my face when I can't quite make out what's going on screen. So it's, okay, all right. Yeah, all right, that's cool. All right, so the subset command is very useful for that. It is possible to overuse the subset command, and I certainly have tried about every way to do so. So we'll talk about that. Now, if I wanted to grab out a particular column, I might do something like this. In this case, I've specified that I want the 18th column of the transcripts. Here I didn't include a comma before it, but I probably should have done that. Here we're looking at all of the p-values, but we're dealing with them in a summary. So we see that the lowest p-value reported is 0, the highest value reported is 0.9994, and the basic summary of it. So you can do some very quick summary information off of individual columns in this way. I would point out that if you do the summary of the whole table, it's going to give you that information anyway. It'll just be part of a larger report. Okay, this talks about how to get a cell from it. Now, the question that most frequently arises when we're dealing with expression data of this sort is, what are my hits, right? We want to know what are the genes for which we saw a p-value of less than 0.05. This is a bad practice because in this case we are using a static threshold against the original p-values without multiple testing correction. But I'm going to ignore that for just a moment. It is a sin that we can talk about at a different time. But we have a criterion here. Again, it's a subset is what we're using. We've specified that we're subsetting from the transcripts object that you read from the CSV file. And we're specifying that the criterion we want to meet is that it has to have a p-value below 0.05. And what comes back is all stored in a variable called low p. I did a dimension off of low p, and I see that it has the same number of columns as before, 19. But now we have just 167 genes that meet this low p-value criterion. Okay, we've already used read table. Now we're going to use write table. I was able to create a new object, a new table with just the 167 rows. And now I'm going to write that out to a new file based on the low p object that we created. It's going to be a new file called low p-values CSV. The separation character will be a comma, and the row names will be turned off for reasons that are not really important, but it helps with the formatting, trust me. So could we have used write.csv? Absolutely, that would work just fine as well. And so when we look in the directory where we're running, mistype. When we do a list of our files, we see that along with df transcript CSV, our input file, we now have low p-values CSV, an output file. We created that. So it's handy that you can use this sort of write table functionality to save where you were in your analysis. This is not the same thing as saving an R object. What we've done is to create a text file that reports the content of an R object. It's not a huge distinction, but it's an important thing to remember that we're going to have to use read table or read CSV to open this thing, but rather than just getting back the R object we were working with. There's a difference, not a big one. Okay. Most typically, when we're looking at gene expression data, we don't think about fold change directly. We use log base 2 of fold change. Does anyone know why we do that? A normalization? It could be called that, perhaps. It's not quite the term I would use, I think. Yes?
The whole change, because in this way we can have small changes and big changes in the same graph without losing the information.
Yeah, that's a good way to describe it. The lowest value for a ratio is 0, and the highest value is unbounded, right? No change would be a fold change of 1. So the changes in one direction are all squeezed into this tiny little space between 0 and 1, whereas the fold changes in the other direction are from 1 or higher. So it's a weird compression to do it that way. If we do a log fold change, log base 2 fold change in this case, then no change is no longer at 1, it's at 0. And changes in the down direction are just as far away from 0 as changes in the up direction. So it's very common then that we look at fold change as a log base 2 fold change instead. So let's work through this. I'm just going to run these three in succession. All right, so way up at the top of the screen, we create a new object called log2 fold change, and we're using the log2 function on the FC column of transcripts. Does everyone read that okay? Okay, so our input to this is the list of fold changes. The output will be a bunch of logs of that. But log2 fold change is just a standalone variable at the moment. It's not part of our table. So I'm going to create a bigger version of our transcripts table that now includes a new column that's been bound to the ones that already existed by sticking the log2 fold changes on as a new column in something called expanded transcripts. So if I were to do a list of what the names of all the columns are in transcripts, I would just say names of transcripts, and then I would say names of extended transcripts. What was it called? I've got the name wrong. Expanded, sorry. Expanded transcripts. Okay, so our original transcripts, this table we read from the file, but now, here at the end, we have log2 fold changes. It's been added on, suffixed on as a whole new column in this table. So very valuable thing to be able to do. All right, what else do we want to do here? I think, so we generated a list of our, the low p-values, but in this case, we're going to just deal with everything all together. Remember that we had all of those columns called FPKM, each of those with a measurement from a different sample. In this case, we need to remember which samples correspond to which cohorts. We have a male cohort and a female cohort in the study, and the table doesn't indicate which is which. So we are using information in this case from the original file to specify that these columns, the 188, 234, 245, 273, 337, 428, and 916 all represent females, and the males are represented by 044, 104, 257, 383, 401, and 454. Okay. So I mentioned, I kind of skipped this first line, but it's worth talking about for a moment. We wanted to not do this for every gene in our table. We specified we just want to deal with row 191 because that's one that happened to visualize nicely. Here I've specified which columns belong to females, which columns belong to males. Those are jammed into those variables. And now we can start doing some assessment of just this particular gene using the cohort information that's provided by the paper. Okay. I can very quickly then just do a quick t-test of these. provided who are the males or the females within these experiments, and now I can generate my t-statistic, degrees of freedom, and the p-value, and we see it's a very, very low p-value indeed. Hopefully, we can also do some plotting with this. Okay. So I have, I'm using a little bit of shorthand along the way here. We've spent just a moment doing a couple of the plot commands, but I think it's useful to see how it's played out here. Sorry. Going to repeat that command. So I'm using the plot command, and I'm starting by putting all of the males on the plot. And that sucks, doesn't it work? We could have put females on the plot first and then added the males later, but yeah, I made an arbitrary decision. I did it wrong. So here we see I have specified a parameter called PCH. This stands for plotting character. We could have just used dots for all the males, but I thought it's more straightforward to actually use M to mark them as male. So here I'm telling it that when I make a plot of these data, I want to do so in a way that indicates who is who, basically. Y lim is something that may seem immediately obvious, but it's worth saying. We're specifying that the limits on the y-axis run from 0 up to 110. I've done that because I'm going to add the females to this plot, and I want them all to fit into the same space. I've also specified that I want an X label on here. Person shows up on the X-axis. On the Y-axis, we see FPKM to represent that these are quantity measurements from RNA-seq. All okay so far? So males had 6 values in it. All 6 of them are appearing here. Hopefully, we can then add more data to this plot, and I'm going to do so just using the points command. Each of these dots is a point, so I'm adding a new series of points to this plot using the data from the females in the study. Again, I'm using the plot character to set them to F, and I'm going to specify that I want the color of those to be red. And now we see that we have the female values all plotted across the top, the male values all showing up across the bottom. So was the t-test giving us a p-value that seems to reflect the data?
Yeah.
Yes?
Very different.
They do, yeah. The p-value is pretty low, 0.0002525. And in this case, I'll illustrate my biases here by saying, when I look at these data, I see that the highest male is still lower than the lowest female on the list. Yeah? So there's a perfect separation. If I just throw a line here, all the males are below it, and all the females are above it. Okay, so this is the kind of indication that we would use to ask, is such a low p-value merited by this distribution? So yeah, that looks pretty solid to me. All right, so we started with the big text file. We turned it into an R object. We added a new column to it, and we've been able to draw some of the data out for visualization. That was the key thing I wanted to do at the end of the lesson yesterday, but I got excited and we spent too much time talking about the other stuff. But is this useful to you to understanding what data go in, how data come out, and how you can look at them? Good. This is not, the way I've done plotting here is pretty old school. The people who are old users of R might have done it this way. But these days, there are some much better packages out there for making much more professional looking graphs. So this is fine for doing exploration, but if I'm trying to go to publication, I'm probably going to want to use some of these better graphical packages for that purpose. Now, for this next exercise, we're going to need to use something called GGPlot 2. We'll talk about getting that installed, but let's kind of walk our way through the next lesson. So this was all from Essentials of R Programming and File Access. I actually want to grab the second one, Boxplots and Jitterplots. Jitterplots is a lot of fun to say. I always imagine the data started dancing. It's okay. Now, I have GGPlot already installed on my computer. You may not. So let's talk about loading a package in here. Do you see this option over on the Packages menu? 2/3 of the way down there, we have something that says install packages. I'm going to select that option. And I'm going to specify that I'm in Greece, so I'm not using the world's bandwidth. I'm just using a local server for doing the download. And I want to find ggplot2 on this list. So you can select that file, specify you want to add it to your personal library, and then it will be installed on your computer too. If, on the other hand, you like the command line version, you can say install.packages ggplot2, like that. And the software will go through those same steps. Now that software has been installed on my computer, it may ask you if you want to use a personal library rather than a system-wide library. This means that if somebody else is using your laptop, they may have a different set of packages installed than you do, and that's okay. Is everybody able to do that? Is everybody able to connect to the Wi-Fi? If you're having trouble with the Wi-Fi, I believe that Daphne has provided the information for today's password for the campus Wi-Fi, so we can get you connected.
You got the raw data. You have no idea which target. Without going through the raw data, how can you explore?
So we can ask, how did I find the example that led to this particular plot? In this case, I used the information in the low p-value table to find one that was pretty close to the top that had a significant p-value if viewed in isolation. So I used that to pick one. But it's certainly plausible that you would instead want to seek out, for example, the lowest p-value in all of the table. That's feasible as well. So you can ask, for example, does everyone know the functions min and max? They work just like you would expect, the minimum value and the maximum value. So in this case, I could say minimum transcripts dot, $sign, is it p dot value? I've already forgotten. Oh. Ha. No, I'm sorry. Let me. Oh, p val. Ah, okay. That's what I was doing wrong. All right. So right away, I can see that the lowest p-value possible in this table was to grab that one. So I could do a subset, grabbing just the fields that had that particular p-value on the row, and that would grab out the lowest one. I didn't do that in this case. I just grabbed one that looked right on the plot.
And this document has been somehow analyzed, right?
Yes. In this case, the software producing that table already did all the difference testing for us. Here we're just visualizing what's already been done there. But you can see that we can retest it, right? We can apply our own statistical models to it and not be limited by what that software had available to it. This is most commonly valuable when you're doing a two-factor study. Here we have the males and we have the females, and we're asking about the differences. But what if you had 4 cohorts that were different on factor A and on factor B? In a case like that, a lot of the main software packages used for analyzing these wouldn't give you p-values that represented both axes, and so you'd want to do it your own way. Yeah. So I'm using the p-values that are computed here as solid and as trustworthy, but for some study types, you'd want to make sure that you had a model that reflected your study design. Okay, has everyone had a chance to install ggplot2? Did anyone get some fantastic errors? Okay, sometimes it happens. I've worked in environments where the Wi-Fi is a little less than steady, and it can be troublesome getting that all together. Okay, second rule. When you install the package, it means it's available on your system, but it does not mean it's loaded. So you have to specify that you want to use that library. And right here at the top of what's called the day 3 script is the command library ggplot2. And you definitely want to run that because it says not only is this already installed on my system, I'm going to use it in this script. So you should just say library ggplot2. If it gives you an error, I think it means ggplot is not installed on your computer. So in this case, we've already read the transcripts file. We don't have to do it again. So I'm going to skip over that line of my script. This next bit is something that we would like to run. All right. It is frequently the case when we're dealing with RNA-seq data. Is there a question I can help with? Is it behaving? Oh, good. Okay. Great. So in this next step, I want to point out that sometimes when we're dealing with transcriptomic data, the transcripts do not all have very clear gene associations. And in this case, I wanted to throw anything that didn't have the gene name filled in, throw it away. So this is mostly to make the data a little prettier and cleaner to work with in this case. So I'm going to specify that gene names are not equal to dot. In the original table, they use dot to indicate there is no gene name for this one, or to say it's the same as the last one. I just want one row per gene, basically. So by specifying that I want to subset out the subscripts so only those with gene names are located, are specified, I'm cleaning it up by that command. And then I can say, I want to grab out the differences. And this time I'm doing it the proper way. I'm saying, I only want to look at those that have a Q value, which is to say a multiple testing correction variant of the p-value. I want only the Q values that are below 0.05. I take that subset and I dump it in a variable called diffs. So if I do a dim on transcripts, oof, I suddenly cannot type. And then do a dim on diffs, I see that both of them have 19 columns, but the number of differences claimed here is only 5. Now, is that larger or smaller than the number of entries we got when we required that p-value be less than 0.05? Does anyone remember? There were more than 100 genes that had p-values of less than 0.05. But once they've been multiple testing corrected, there's only 5 genes that have a p-value less than 0.05. Another difference here is that we have already screened out anything that doesn't have a gene label on it. So that would also be a difference. Okay, so now we have a list of differential genes. In this case, one of them is a very, very big difference in intensities, and I wanted to get rid of it because it makes our plots look a little weird. This is just for illustrative processes, so I'm going to run this next line, and it's going to throw out one of those genes, and now we'll have only 4 genes that had this great difference. All right. Now here's a slightly different operation. In this first case, I ran the dimension function on diffs, and it said I had 4 rows and 19 columns. But in the next case, I wanted to say, how many rows are there? In this case, I still ran the dim function, but I've got this weird square brackets 1 business after it. You see that? What this is saying is that I know multiple numbers come back from the dim function, 4 and 19. In this case, I only care about the first of them, the number of rows. So numDiffs is using dim to grab both dimensions, but then grabbing out just the first of them. You can do a lot of tricks like that in order to jump to a particular bit of information from a function that returns multiple values. All right. Once again, we need to make an association between the cohorts that are represented in these studies and the columns that appear within the table. In this case, I am using a column called fastq to specify which of the experiments yielded each value. So the fastqs that are available here are these numbers. It's just a way that I'm grabbing out those particular columns, essentially. I'm going to specify a sex that applies to each of these samples. The first 2 are male, the next 2 are female, then a male, then 2 females, 2 males, 1 female, 1 male, 1 female. Where did this come from? Well, there's a file that appears in the same directory as the table called Juvada's Phenodat. In this case, they've named what each of these columns are and what they represent in the original study design. These are metadata to tell us which which experiments relate to which sample. It's pretty important information to have. And very, very frequently, that information is missing from the data that get uploaded. So be very kind to people who want to reanalyze your data. Give them the metadata. So I'm pulling this information from here in this way. All right. So I see that they use data from multiple world populations, YRI, GBR, I guess those are the only two here. But we're going to grab all of this information and put it into a big object, basically. So let's grab all of that and run it. Shouldn't have a problem there. Okay. Now, let's look at the variables that came back. FastQ. Oops. If I type FastQ, I see that it has 12 values. Yeah. So we had 6 males, 6 females. FastQ is going to be a long table, a long vector of those values. We created something called sex, and we see that there are more values of that. So let's say what was the length of sex. We had 48 values here. Okay. I'm going to explain how this works in just a minute. And then we had population. And again, we have 48 values of that. All right. What we're going to do is a reshape. Now, how do I explain reshape? Remember the table that we began with. Here we have just 4 genes, so we don't have to deal with the huge number of rows, just 4 rows. But we have 12 different samples from which they came. We've now annotated which of these are males and which of these are females and given it an experiment name. And down the side, we have different genes. So we have 12 columns and we have 4 rows. All good so far? Okay. This is what we call a wide table because for each gene on the rows, we report every intensity across the columns. But the ggplot library doesn't particularly like data in that format. It greatly prefers it when the data are a narrow format, not a wide format. So we're going to restructure the data. So yeah, this is exactly a transform of the data. We're changing this into what's called an EAV format, expression attribute value. So imagine if instead of showing every sample for every gene, you instead said, this for this person, for this gene, we had this value. For this person, for this gene, we had this value. This is what we call turning the wide table into a narrow table. So these next commands are going to do that. We're using the reshape command from ggplot to do it. Okay. So what happened when we did this? Let's look at long diffs. All right. I'm going to throw away the plot for just a moment here so we have more space on screen. Okay, long diffs. Yeah, so dim long diffs. Capitalization does matter. Okay, so now we have 48 rows and 4 columns that have come out. If I look at just long diffs row 1, okay, row 1, I can see a fine example of this. So why did I call it time? I don't even know. All right, so we have the gene name, we have the time, and this is an PKM value that comes from 1884, and we've got some number that relates to it. So the data are stretched relative to what they were originally, but it's the same information just represented in a different way. Let's move ahead. Right, so we now need to do a little bit of renaming. That's why I had that in there. Okay, if I look at that, that's much better. So after getting all the renaming stuff in place, gene names is in the correct place. The FastQ that it comes from, which experiment, is in the right place. The FPKM value and the ID number are all reported properly. Okay, this is great. So now we've restructured the data in such a way that we can make our plots more easily. I'm going to show just a few of the values that come from this. Head. Remember, you can look at the top or the bottom with head and tail. So here we see the very top of this 48-line file. We have different gene names for the same individual with these FPKM values and these ID numbers. That's all good.
The ID numbers are incorrect. It's repeat one before.
Yes, I think in this case, the ID numbers are specifying which gene, what's the gene in question that's being visualized. All right. And the sound of the saw is back with us. We'll simply deal with it. All right. So now we're adding on the metadata that came with it. What happened? So we had a quick look at long diffs. Let's look at extended diffs that we just created. Now we see that the sex and population information that were provided in the metadata file have been glued onto the left side of this table. Right? Now, finally, we get to grammar of graphics. Now, grammar of graphics, you can read whole books about how the ggplot library works. I find it's a little difficult to get started with, but it's very frequently worth your time. If you're going to produce plots from R that you intend to use in a publication, ggplot 2 and its support libraries like ggpub can go a very long way towards making your graphs look sharp. So it's a very nice thing to know how to use. We see that images have different layers of information that we're combining. Data. Quite obviously, you're going to need to specify some object that provides the information that you're visualizing. That's the data aspect of it. We have aesthetics. Naturally, I'm a very aesthetic instructor, right? So we think about what are the things that make our data produce a visual presence from them. That's the aesthetics, right? Then we have things like scale. Will there be some sort of mathematical transformation? Are you going to use a log scale? Are you going to use a linear scale? Do we need to add breaks in an axis? That sort of thing would be considered part of scale. And what you frequently hear called geoms, or which geometries are going to be used. What kind of coding are you using in visual space to represent your data? A moment ago when I gave you the big plot that had M's and F's on it, that's an example of M and F being used as geoms to represent the data. Okay, statistics. It may be that plotting the data themselves is the right option, or it could be that you want to produce some sort of summary, like a box plot, for example. Facets, it might be that you want to create one of these massive figures that show up in like Nature and Science, where you have 20 panels for one visualization and everything is shrunk down to a pinprick. Yes, you can do that with facets. And is there some sort of coordinate system that applies? Maybe you're using Cartesian coordinates, but maybe you're doing something that requires polar coordinates. ggplot can handle all of that stuff. So these are the kinds of layers that we use to build up an image with ggplot. All right. So let's start with a Dynamite plot. Dynamite plots are very frequently excoriated as a terrible, terrible thing that no one could really love. And this is an example of a Dynamite plot. Why do we hate Dynamite plots? Let's start with a very basic question. I have this bar representing females for PNPLA4, and I have some value measured in FPKM. So I've got this value right up here. What is the height of this bar?
Around 90?
Yes, on the scale it's around 90. But what does the height mean? Yes?
It's the mean value of the points, right?
Okay, so he's asked the question and answering my question, which is very useful to know. He said, it's the mean value of the data points, right? So some people will give you the mean. Some people will give you the median. Is there an indication on this graph which one they did? No. Next up, what about the whiskers here? I've got whiskers that go up and whiskers that go down. Are they the same value? Is this one going down as far as this one is going up?
Yes.
Yes?
It looks like it.
It looks like it. It looks symmetric, so maybe it is. Do they represent an interquartile? Do they represent,
As
sorry?
the
Does it represent standard deviation? Does it represent... The reason why people hate these plots is that none of this is specified, and you could use lots of things. Standard error, standard deviation, you could use interquartile. If the researcher doesn't tell us how to interpret it, we have a lot of guessing to do. But the reason statisticians really loathe Dynamite plots is that they don't provide very much information, and they use a lot of ink. So let's look at this. How many points are represented? How many numbers are represented in this particular bar? We have the mean or median, yeah? If these are symmetric, then we have something representing error, maybe standard error, maybe standard deviation, I don't know, one of those. So this bar and these whiskers are exactly 2 numbers. It's pretty disappointing. So it's using a lot of space, but it's not giving us a lot of information. So Dynamite plots are evil for this reason, and if I'm peer reviewing a paper, I'll ask something like, how many replicates does this represent? Because I can't tell. Does the plot tell me how many replicates there are here? No. There were 6, remember? That information's just been lost by visualizing it this way. And yet people use these plots all the freaking time. All the time. And they upset me every time. Okay. So now you've listened to a screed about why we shouldn't use Dynamite plots, but what's the alternative? Let's look at this. So I have some questions here. I think we just went through those when I was yelling about the data. Let's now look at a box plot using ggplot 2. I'm sorry, I never actually looked at the ggplot command up here, so let's spend just a moment with that. Remember, we had geoms and we had data sources, and aesthetics and stuff like that. So we ran the ggplot function specifying xdifs, the extended diffs table, as the information source. So that's the data layer. We had the AES function in here. That is the aesthetic function being applied. And we specified that where we were on the x-axis was going to be the gene name. Where we were on the y-axis was the FPKM, the quantity by RNA-seq. I'm sorry, that's a terrible way to describe it, but that's what it is. And then we have the fill color of those bars that's representing sex. So the males and females of the study were represented by blue and red because I was very unimaginative. Okay. I mean, I might as well use like pink and pastel blue, right? That's gross. So yeah, so that's our aesthetic that's being described for this visualization. And in this case, we are not plotting the data themselves. We're plotting statistical summaries of the data. Literally, the stat summary function in this case was producing by using the mean function. Good call. Your assumption was correct. It was using the arithmetic mean. It's using a geom called a bar to show that data. And the position is called Dodge. Are we suddenly driving American cars? No. The Dodge function says that if you've got 2 things that are supposed to go to the same location on the x-axis, push them apart. That's what made the male bars go one side and the female bars go the other side. So the Dodge function here says, don't overplot, put them beside each other instead. Don't add them together either. Put them beside each other. Then, in the y-axis, we're using another statistical summary, here using the mean underscore SE. Everyone sees that. This is the standard error. Why do people use standard error to represent the whiskers on a Dynamite plot? Does anyone know? The answer in almost every case is that standard errors make your variation look smaller than if you use interquartile or you use standard deviations. So if you're trying to make your data look consistent, use standard error. And so almost everyone who's making a Dynamite plot does that. It's wrong, but this is what we do. All right, so those are the error bars that are being used to represent the standard error. And again, the positions are dodged so that the males and females are over the corresponding bars. All right, now let's do the box plot instead. We'll start with a quick, just running of the code here. Okay, back to the console, type in command. All right. Same data, different, right? Now, what we have are boxes showing up for each of these. They have a midline, they have a top line of the colored region, bottom line of the colored region, and they have whiskers pointing out from those. We have the same color scheme, because we didn't change the aesthetic on that. We have the same x-axis, the aesthetic didn't change. We have the same y-axis, the FPKM. It's the same data, but plotted very differently, wouldn't you agree? Okay, so let's talk about why we would do this instead. All right. You can see that the way we had to call this was quite different. The aesthetic was exactly the same. X equals gene names, Y equals FPKM, fill equals sex. That's all the same. But now, instead of specifying the two stat summaries, we're specifying we're just going to use the geom boxplot defaults. So we have more information being presented about each gene for each sex. We have the middle point, we have the upper edge of the bar, the bottom edge of the bar, and the whiskers. Again, you would need to know what are the default behaviors of the boxplot function to be able to put a meaning to each of those. How are you doing on watching the time? I'm not running too long yet. We're still good.
I'm taking the day.
Okay, he's got our lunch timers in his hands, so this is a very important skill. All right. So, do you know from looking at this box, at these box plots, what number of replicates we had?
Maximum and minimum.
Sorry?
The maximum and minimum.
Okay, so we know the maximum value, we know the minimum values. When we show the median, this midline, does that represent a particular measurement for each of these genes? No. We had 6 replicates, so the median is actually the average of the middle two. But we do have the way to show a very, very large amount of data could be thrown at this, and yet the box plot would be able to show us the distribution of those data. How would you evaluate the spread of the data for males for a particular gene? You would basically say, are these edges far apart from each other or very near each other? That's called an interquartile, and in a box plot, the top and bottom of the colored region is almost always the 25th percentile and the 75th percentile. So if that box is quite wide, it tells you that the middle of the data has a lot of spread in it, and if those values are quite close together, your data have very little spread in it. But it's still not quite as good as showing all your data points. So how would you do that? In this case, we are able to add new stuff to an existing plot. Yes, we're finally getting down to the jitterplots, the data dancing. So we're going to redo everything we just did, but now, instead of having boxplot run as default, we're adding a dodge command to it. And we're adding a new geom, a dot plot, on top of it. Let's look at what happens. Okay, it's probably not the way that I would want to send this out for publication. But it has both a statistical summary of the data and the original data points themselves. So now we have these dots to the side. These are actual measurements drawn from that table. And we see that over here, we had one value way the heck up there. It wasn't included in the box plot because by box plot analysis, that's considered an outlier. So now that dot way up there is something that we're capturing by showing the data points overlaid with this. We see that very frequently, a lot of these values are all piled along 0. If you've got a gene on the, if you have a gene on the X chromosome and the X chromosome is inactivated, you're going to get a bunch of zeros, right? So sometimes you'll find that values are very close together, and the jitter plot will jitter them to different positions along the x-axis to reflect that these are all ties, essentially. In this case, having both the box plot and the jitter plot on the same space makes it look a little cluttered, if you ask me. And so we can make this graph a little bit simpler by just doing the jitter plot itself, by doing the dot plot without having the box plot summary there too. And when we do that, we have these data. Now, is it always the case that you want to plot all the data points?
If there are too many data points, there is no need to plot them all because they will clump together and nothing will be.
Sure. If you had 100 replicates for both cohorts, the data would start packing in there and be pretty messy. It might still be quite usable at 100 points, but at 1,000 points, it's not. So you can visualize that using something like the box plot, but more advanced stuff like violin plots are also available to you here. There's a world of graphical formats available to you within GGPlot, and it's happy to show you what this or that would look like until you feel you have something that's a good representation of your data. Any other questions before we move ahead? Okay. I feel like when I talked about reshaping the data from a wide table to a narrow, tall table, I went pretty fast. Do people kind of get how that worked? For the purposes of GGPlot, having your data in an EAV tall and narrow list is very frequently the option. All of the genes are listed in different rows down this very long list, but because GGPlot knows that there are different gene values represented there, it's able to split them out appropriately because it knows what their names are. So it's a useful way to visualize it, but it's not maybe the native way we're accustomed to thinking about it in spreadsheets. Turning it into a narrow format is unusual for that. All right, I had a few more things in here. Oh, of course. At the end of the day, you've got a figure that you actually like, right? But how do you get this into your poster? Are you going to screenshot it out of R? I mean, you could, but that's not the good way. So let's look at a couple options. Let's start with making a PDF of the thing. All right, so the first command here, ggsave, is how we turn the thing on the screen into a file. Is the file going to be identical to what you saw on screen? No, it's not. Because you may specify different dimensions for what's going into the file than what you have on screen. So if we see the command here, I'm going to write it to a PDF format. I'm going to specify a width of 14. I forget whether that's 14 inches or 14 centimeters by default. Oh, it's centimeters, good. Okay, so the width is 14 centimeters, the height is 12 centimeters. Here I specify those units are centimeters. And if you look in the directory, you should have a brand new file called jitterpdf. Here it is. So, looks all right. Maybe I want to change the font sizes and stuff like that, but often you can affect all of that by just specifying on my poster, this is going to be 10 centimeters wide and 6 centimeters tall, and it will automatically adjust all that stuff for you. So rather than forcing your figure to look right for the shape it's going into, specifying the shape it's going into can automatically handle a lot of that stuff. Now, is a PDF easy to post into, say, PowerPoint? Yes, you can. Under some versions of PowerPoint, you can get away with that. Some older ones will fight you on it. So you might want to produce a bitmap version of this, a GIF or a JPEG or something like that, or you might want to write an SVG. SVG or EMF is often a very good format for that. GGPlot supports all of that stuff. So it's generally pretty easy for you to pick a format you want to put it in. The next command I had on the coding example shows you how to make a bitmap from it. So let's look at that. Okay, so I've just now run the command here. If I open jitter.png, I see that my graphics editor can open that. So I don't like that there. I can just remove it, right? I can't? Can I? Not really. You should have a structured and described method for removing outliers. You shouldn't just go into your graphics editor and just sort of mark it out. That's rude. And you could be accused of malpractice for that. So
Cut down.
oh, just crop the whole figure off. Yes, you could do that. But we see that already, just by going to a PNG of this dimension, the relative sizes of the fonts have changed, haven't they? So if I look at the same image saved as a PDF or saved as a PNG, the software's changed how this visualization works because they're different relative sizes. The command that we used here specified a width of 1120, a height of 960, but our units have changed. What's px?
Pixels.
Pixels, right. So when you create a bitmap, like a PNG file, we have an explicit count of how many dots there are across and how many dots there are up and down. You can also specify things like dots per inch to make it ready for publication in a journal. Great. So now we have the ability to load a table into memory from a text file. We have the ability to pull out little bits of it. We've explored a base R approach for making some plots from it. But more importantly, we've talked about GGPlot 2 as the grammar of graphics approach for making high-quality graphics for publication. We will talk a little bit more about plots that are specific to gene expression types as we go over the next 2 days. And we'll be looking at how those visualizations work. But I really appreciate that everybody could hang with me as we got into this place, because we were using a little bit of material from yesterday to add that into today's lesson. So I'm glad we could do all of that. And at 11:15, I believe we are, at 12:15, my clock is still Central Europe. We see that we are done with 15 minutes to spare. So we'll have to see if the caterers are here and our lunch is ready. But thank you for being our alarm today. And I hope that this was a useful insight as to how we get visualizations done and why statisticians care so much about visualizations. So I hope that was useful to you.
Great.
Thank you.